branches.
There are, yes. I thought parentheses would take longer, but they didn't. Alright, well, let's do it. So hello again. Today we are talking about arrays. So previously we added support for variables that are local to function scopes, but not other scopes. So previously our iterative factorial function here had a bug in it where that while loop would not actually assign to the x, but now it does. And we can see that at the bottom, that the iterative factorial and recursive factorial do return the same thing, so that's cool. And arrays have been a long time coming. I've been talking about them for a couple weeks now. And today we're finally going to add support for statically allocated arrays. And also we're going to just do parentheses while we're at it. So we can see here that we define an integer array with length 10, and we assign to it, and we retrieve from it, and we've also got a parenthesis expression down here. It's starting to look a lot like real C code, which is very cool. So in LLVM, arrays are actually their own data type, whereas in real assembly, everything is just binary. So that's kind of a fake representation. At that point, array is like an abstraction, and we've kind of just arbitrarily agreed that contiguous elements in memory are an array, whatever that means. But in LLVM, you have an array data type. So we can see here that when we're declaring an integer array with length 10, we say allocate 10 times I32s. So that's that. And when we access from it, we have to use this get element pointer inbounds, etc. thing that we used for addressing things earlier. And the downside is that we have to account for this. We have to work around this. There's no other way to do it. There's no other way to do arrays. You have to do it this way. But the upside is that it's way more secure. Clang is going to handle a bunch of stuff that our compiler users are going to do that they shouldn't be doing, and it's going to throw errors, and that's on the Clang side, that's not on our side, so we can't really do anything to let those users do funky array stuff that they shouldn't be doing. So accessing out of bounds of a statically allocated array, like stuff like that, it's going to be handled for us.
So in C, if you access out of bounds of a statically allocated array, what would happen?
It would access memory outside of the array bounds.
But our language won't do that?
I'm pretty sure it won't. Pretty sure. I haven't tested.
So there's no way to actually go around this and just use raw pointers?
Once we start calling the C standard library, yes, we will be able to. But for now, arrays are their own data type. They're independent, and we'll see what ramifications that has. And we can see here, so when we store into an array, we get an element pointer, but that %7, that's a pointer. So we can store directly into it. And if we actually want to use the value, we have to load the pointer that we get when we access the array. So when I was following ACWJ's approach to adding this, I noticed that about halfway into implementing it, I realized that we had to go a different direction. So the way ACWJ does it is they treat arrays strictly as pointers, and vice versa. So pointers are arrays are pointers. And that way, array accesses using the bracket notation that we're familiar with are basically just a parsing problem, where you're using dereference and addressing stuff that already existed that we could have done previous lectures, right? That's nice because we can basically just reuse all of our code for that. We don't have to do anything special. And it's also nice because it automatically treats arrays like pointers. So we can just hook into the C standard library, we can get a pointer, and we can we can do whatever, and we're fine. We're good. It's not nice because that isn't how LLVM arrays work, which is frustrating. Our approach, as I said before, involves treating arrays as their own data type, not pointers to whatever root data type they have. And additionally, we're going to have to define a new meta token type for array accesses. So our version is nice because it is conducive to LLVM's array representation, and therefore we get all that security that LLVM gives us. It's kind of nice that we can reuse some of our logic for addressing and dereferencing, but we are going to have to write a fair amount of custom stuff. And it's not nice because we can't treat arrays as pointers at all unless we actually extend our implementation later on. So we will not be able to do this notation right here. In fact, any use of the identifier that we declared for an array for now will have to be followed by bracket accesses. So you can't even say like, array A or int array 10, int array B 10, array B equals array A. Like, we're not going to be able to do that. You can't assign an array to anything.
So how would you go about passing like arrays into functions? Because I can see you would pass the pointer.
So we can't yet, but with statically allocated arrays, you can't do that anyways.
Oh really? I thought you usually just like pass the pointer to the array. And since it's already a pointer, it just.
Before I say something incorrect, let me just.
Like instead of that in the function argument, you would just do int pointer. That's equivalent.
Say again?
I don't. Well, okay, you can just try this.
Ooh. Okay, so it's passing by value. I thought it didn't do that implicitly. Okay, short answer, you can't.
You can't do what?
Can't pass arrays into things or return them.
I thought you just passed the pointer instead of that.
In our compiler, we can't.
Oh. Okay.
In this, yes, we can. I was under the impression that if you statically allocated an array, it would not. You wouldn't be able to pass it into stuff because it exists on the stack and not the heap. And there's a new stack frame for the called function. But if it's passing by value, then I guess it'll do that automatically for like int arrays with length 10. But if you have like a struct array with a bunch of different stuff in it, I don't think it's going to automatically pass by value. I don't know. I have to look more into that. But for our intents and purposes right now, arrays will only exist in a local scope. And I do want to expand this in the future, but given the amount of time that we have left in the semester, I do want to prioritize other things, so we might not fix arrays. Still up in the air. But here's the plan. So we want to update our expression parser to respect parentheses. We need to create a new array type, whereas before we just had numbers and functions. We need to add parsing and generation for array declarations. We need to add parsing and generation for array accesses. And that also allows us to parse for array assignments because we changed how L values work. And we also need to make it so that the LLVM value class distinguishes between array values and number values. And just a couple tiny things. is that in a bunch of places in LVM.py we had like LVM value dot number type, LVM value dot references, LVM value dot register name. We had that like in like 15, 20 places. So I just condensed it all down into one function that that the LVM value has. So that way we're not reusing code everywhere. And then I had to add in the long type because all array access offsets are I64s in LVM.
What do you mean by offsets?
So when we get an element pointer, so if we have this index I that we want to access, this is this right here, I64%6. We load I, we extend it to an I64, and then this is our offset.
So indices of arrays are I64s.
Yeah. And I'm pretty sure this is like the dimension of the array. So if we have a matrix and we want to access something, if we want to access like a row element, or if we say like matrix IJ, this would be J, this would be I. And I think that for multiple, like 3D or 4D or whatever, I think you would need to chain these get element pointer statements because they only accept 2 I64s.
I wonder why they made an I64 for the indices.
I wonder also, but I don't know. But
This seems like a really large value.
Yeah, I guess.
For the size of an array.
Well, so it is the maximum value that any CPU, any 64-bit CPU is going to have as like an address boundary, right? So even if you have like a pointer to a giant struct, I don't know. Well, yeah, it would be maximum 64 bits. I don't know. Yeah, I don't know. But that's what they did, and those are they have to be I64s. I got errors when I did it the other way, so that's what we're doing. So let's just look at the code because it reads a lot better than a presentation. This is the entire update for adding in parentheses. That's it. This is inside of parse terminal node. So anytime we see a left parenthesis, match it, get a binary expression, match a right parenthesis, return it. Boom. That's it. That's all we need to do. It's great. Additionally, I updated the arithmetic test generator. So now we do have the division operator, and I just do a try except to see if it divides by 0. That works. That's nice. But it's also going to use parentheses randomly, so that way it's not all like left associative or something, and so we get a nice random distribution of tests to run. I guess I'll just show what the tests look like. This time echo tests. Is it an example? Oh wait, no, it's right there. So it I must have changed something. Okay, it wasn't doing only left parentheses, but okay, yeah, I'll fix that. But it was doing the right thing earlier. I'll fix that soon. But that's nice. We get better test coverage, so that's good. Looking at this, yeah. So let's look at the array type. So this is the new array type that I added. It contains a number object that determines what data type is being stored in it. It's got a length. It has a list of contents. This is currently unused, but eventually we will use it when we have initializer lists. And it's got a dimension, which in retrospect should be a list of integers, because this would really only help if we want to declare square matrices. But again, this is also unused, so not a big deal. One thing that I found was interesting is that C does let you declare length 0 arrays. And that's annoying to me because that's ridiculous. What is a length 0 array? Is it even a pointer? I don't know. But I want to stick with the standard, so we're going to allow people to declare length 0 arrays. But that's frustrating to me. We'll generate a list of contents if it doesn't exist, and it's just going to be filled with zeros. We don't use this contents list at all yet, because LVM already does zero initialize lists for us, or arrays. However, I have in mind an idea for some optimizations that we could do if we had initializer lists.
I don't understand what the purpose of the contents thing is, because if you initialize it, it can change later.
Yes, but you can do optimizations before the changes. If there's just like you can optimize out array accesses. If there's an initializer list, accesses, then changes. So I don't know. Also, it's just nice to have information about what the user is doing, because maybe they're trying to do something that they don't mean to do or something. I don't know. It's generally, when you're writing a compiler, it's nice to just have representations of whatever the user's doing. You don't want to leave it all up to runtime. So, and then it's got a reference to its number type and its pointer depth. And this is its LVM representation, where it's got a length, x, and then whatever the number's LVM representation is. Next thing, parsing. Okay, so this is in our declaration statement. So this is being handled by the same stuff that was handling our regular variable declarations. But basically what we're going to do now is we're going to check and see, do we have a left bracket coming after this variable name? If so, we're going to match it. We're going to require an integer literal for the size. We could allow binary expressions that only contain integer literals. That would be fine. However, that's like annoying to do. But you can't do dynamically, like if you've tried to do like int x or int x array, like I don't know.
Yeah, you have to get malloc.
A equals whatever, yeah. Int xa. That's not allowed. It doesn't let you dynamically allocate arrays like that.
But in Java you can, right?
Yeah.
I was very surprised at that when I learned Java for APCS, because I learned C++ first.
Mm-hmm.
It's like, oh my god, you can. Pretty cool.
It's nice, yeah. I'm a little surprised that most C compilers don't let you do that and just do the malloc for you. I don't know.
I feel like I would want to know. Like, I don't want my C language to manage memory for me. Like,
yeah.
Unless it's very explicit.
That's fair, yeah. Yeah, so we're going to require integer literal. Eventually, we're not going to require an integer literal when we add in initializer lists, but for now, we just have to say they have to have a constant size. Match a right bracket, and then we're just going to generalize the number. Or initially, types took in a number, and now they're going to take in either a number or an array. That's what we got going on there. That's it for that. Array accesses, okay, so token type. So we had to, obviously we added in our bracket tokens, right? But we also had to add in an array access type. And let me show you why. So this is the function that I wrote for array accesses. And let me get ACWJ. What they did is right here. So they get the address of whatever array we're accessing, and that's its own AST node. So it's going to compute the address of that. It's going to scan in our brackets. It is going to grab a binary expression, close the bracket, and then it is going to add whatever it got inside of the bracket to the address of the array that we're accessing from. And then it's going to dereference all that. So that's going to get us something like, right? And that makes sense. So I should say array. The address of the array, that's going to get us the address of the first element. Add 1 to it, and you'll get the second item in the array. Add 2, you'll get 3, etc., etc. And then we want to dereference whatever pointer we get from that. And that makes sense for ACWJ because x86 does not discriminate between an int pointer and an array. They're the same thing to it. We don't have that liberty, and so I tried doing this initially, and it ended up being a ton of like extra optional logic in the array access and or in the dereference and the addressing functions in LLVM.py. And it got really, really messy really fast, and it didn't work as well as it should have, and so eventually I said, enough of this, I'm just going to do it a way that LLVM is more comfortable with. That's what I did. Let's see. So if we have an assignment statement, which can I get? Yeah. So if we have an assignment expression and we see a array access, let's just store into the right virtual register, which is going to be a pointer that we got from the get element pointer call, right? So just let's assume we have the get element pointer, we've got the array access already, and we're assigning to whatever we accessed. Just store local into it like a regular pointer. And that works just fine. The other thing is actually accessing the array. I have to expand the diff. So what this says is, make sure that the symbol table entry is actually an array. We want to resize whatever offset we get into a long. And then we want to get element pointer in bounds, whatever the type representation of it is, or whatever the type representation of the output is, whatever the LLVM representation of the input is. So that's going to be the type followed by the $sign and then the name of the register. Just statically, we're going to say, we only have one dimension for our arrays, and then we are going to give it the offset. So do we agree with that? That is what I showed right here. So that's what we just did. And we have to implicitly increase the pointer depth by 1. I mean, I should have done that right there. But yeah, so this is going to get us a pointer to something in the array. So if it's an int array, we're going to get an int pointer to whatever we accessed. That makes storing nice, but it means that if we actually do want to access that item and use it in a computation, then we have to load it one more time. But that's already handled by our arithmetic expression stuff, because it's going to call ensure loaded for us. Okay, so let's look at the LLVM value class. Not a huge difference, but I added in this array object that you can pass into it. And that's just going to tell itself, I'm not a number, and this is what my array length is. And the reason we need that is when we're generating the type representation of it, we need to check, are we a number? If so, let's just give it the number type and the references. Otherwise, if we are an array, then we have to use this bracket notation, and then we can give array length, and then the number type, and then the references. Yeah. And yeah, these are the just quick fixes. You know, this is stuff that we've seen before a bunch of times in LLVM.py. But now it's just nice to be able to say, give me the display value instead of, percent if is virtual register, then the int value, and it's just, it makes everything simpler.
Yeah, I did that in C.
I don't blame you. It's a lot. It's a lot of extra. I put this off way too long. I should have been doing that from the get-go. But yeah, so that's it. That's what we did. You've added the char type, right?
Yes.
So you know what would entail adding a long type.
I added it for the picture fit thing.
There you go. Then we're good. There's nothing else here. That's it. And I'll show you the test I wrote. What's
the optional homework?
Yeah. Okay. So that's the array test. We're gonna build an array that is the numbers 0 through 20, skipping every other number, or 0 through 18, skipping every other number. And we'll print the index and then the item of the array as we traverse it. And then we're going to do an assignment to an expression that has parentheses, and then we're just going to print, getting out of the array. Scripts run, examples, test arrays. Bam. So for 0, we have 2 times 0 is 0. For 1, we got 2 times 1 is 2. And it goes all the way up to 9 and 18. And then down here we say that A8 is going to be 3 plus 5, that's 8, times 2 is 16. Boom, we got 16. And so I'll tell you a cautionary tale about my first attempt at implementing this, and the reason I had to delay this lecture. So when I originally wrote this test, I did not put this 2 times. I just said AI equals I. Very simple, range function kind of, right? And I still had the x equals AI, and I still had all these prints and stuff. And I did the implementation that ACWJ did, and it worked. And I was very surprised, and I was not expecting it to work. But it printed out 0 through 10, and that was great. And I was super excited, and I looked into the LLVM that generated, and the thing that really surprised me was that it seemed that the compiler was optimizing in a way that I didn't understand. Like, I thought, wow, it's finally gotten so complex that it's doing things that I'm not sure why it's doing. The thing it was doing was that it wasn't actually assigning to the array, and it wasn't assigning to X either. So these didn't even generate code, and then this executed normally, and then this acted like a print int I. And my first very naive thought was, wow, I've designed a system so smart that it knew that all it needed to do right here was print out I twice, and it didn't actually need to do any assignments. And my thought was that it's probably got something to do with like the latest LLVM value thing that we had for local variables. And I accepted that, and I said, okay, cool. But as I started thinking about it more, I was like, maybe it's not that smart. And I wrote a better test, and I put some complex assignment here. Actually, I might have just put AI equals 0 or AI equals 1 or something, and it broke. And it didn't like that, and I realized, no, my system is not that smart. In fact, it's very dumb. It doesn't even know how to do real array writes or accesses or anything. And so that's when I realized, oh, I actually do have to, I should take a different direction. I should, deal with arrays more naively, but they'll work. And that's what I want. I want them to work at all. And yeah, so that's how we ended up here. For the next lecture, I'm kind of torn. So I want to do C standard.
That's a question. If you do print it, instead of X, you put A index to I, would it work?
Let's see. I think it should, but who am I to not test it?
Oh, you did it below too.
That looks right to me. Cool. So next lecture, I'm a bit torn about. The issue is that I want to do C standard library. And that's going to tie in with the preprocessor. Because the preprocessor is going to let us define functions, or the preprocessor is going to define all those functions that we're expecting to get from the standard library, right? But there's an issue. The issue is that the preprocessor is going to generate a bunch of typedef statements. We haven't implemented those yet. We can implement typedefs, but when we implement typedefs, in addition to typedefs, we also have to get function declarations, but not definitions, so just the header. We need to do that also, because that's another thing that the preprocessor is going to spit out. And so the very minimum, we have to do both of those things, and that's going to be a little annoying. And I'm curious, should I just get it over with and let's do all the boring stuff, and then we can finally have access to the strength of all those C functions? Or should we add some more operators, maybe add structs, do like more obvious, like this is a new feature to the language? So I'm curious, what would you prefer?
I don't actually know.
Mm-hmm.
I feel like I would like to be able to malloc.
Okay.
Make it Turing complete.
Mm-hmm.
I feel like it's pretty essential for a language.
Yeah. Okay. Well, I'll start on preprocessors then. Thankfully, we're not going to be doing a preprocessor. We're just going to call Clang, and it's going to do it, and it's going to be wonderful. We'll just have to. Preprocessors have a different comment syntax, so that they use pound signs, hashtags, whatever. So we'll have to do a little bit of updates, but nothing too crazy. So, anyways, that is it. Any other questions?
I was just curious if you worked on the O0 at all.
No, I haven't. If you want to push a fix, I'll merge it.
I might be able to.
Okay.
Because my compiler defaults to O0.
Yeah.
So I found them just working on it.
Mm-hmm.
Maybe I could push a fix. Like I fixed an issue on mine.
Mm-hmm.
I think there's another issue, but I just haven't looked into it.
Okay. Well, yeah, it's on the list, but when I'm considering should I fix a bug or should I write the next lecture has to take priority. So. Cool. Well, let me see if there is optional homework I can give. I don't think we can yet, but I think next week there probably will be. Are you up to date on lectures?
I'm not. I still need to finish lecture 14.
Mm-hmm.
But I'm caught up other than that. I don't think I'll be able to even work on lecture 14 or 15 this weekend.
Okay.
Because I have a lot of work.
Okay. Character literals. So, standard ASCII characters and also escaped characters. Yeah. So that's the optional homework for this week. I'll add it to the slides and re-upload. But yeah, cool. All right.